Hello, hi to everyone. Welcome to our channel. Now we are going to discuss in this particular video chapter number 5 Boolean algebra. So this is one of the important chapter in the KVS examination. We can expect one or two questions from that. It is a small chapter also. So I will give the introduction about this particular chapter. Then we are moving to the complete discussion. So this Boolean algebra, one of the scientists, pioneer scientist, George Boole, is a 1985 to 1964 is a period. So he introduces this Boolean algebra. So in the Boolean algebra, it is a logic, algebra of a logic presently are operation in the computer devices. All the computer devices we are operating, we are using this particular logic. Okay, that means what we are operating the digital, this total entire the basics of digital electronics. These basics we can AND gate, OR gates, what we logics we are using the computers, it is useful for you. In the second one, starting with the investigation, actually 1854 mathematical system of logic which can be expressed in the truth functions. Truth functions means we have a truth tables for each and every operations, maybe AND gate, OR gate, NAND gate, NOR gate, XOR gate. So different we have using the different symbols also for that. So you are manipulating, he can conclude some symbols to arrive at the conclusions. Okay, in this new system, it is not like a ordinary numerical algebra. Ordinary numerical algebra, in your high school, in your 6th to 10th standard, the some algebraic equations. So those are the ordinary algebra. But what we learn here, that is a completely different from that. That's why it is a new system of logic algebra. Got my point, right? Now, what are the unique features? So this particular Boolean algebra have a unique features. What is the unique feature? Let us see. In case of normal algebra, for example, you are taking 2x plus 3y is equal to z. For example, you can take x value, y value, z value, any value. You can take it and check the equations, no problem. Those numbers are real numbers. But in the case of Boolean algebra, particular equations, only you are using 1 or 0 or 1. Only two cases are possible, 0 and 1 state. Okay, for example, you are taking a plus b is equal to c. The a, b, c values you can represent it either 1 or 0. That is a unique feature for this Boolean algebra. Okay, so to identify this total all these functions, we can operated some laws are there. Those laws are very important. Throughout this particular chapter, maybe we are going to discuss about digital electronics. If you are perfect on the digital electronics, if you want to get the 10 marks out of 10 marks related to the digital electronics, you need to learn these laws completely. You need to by heart, or you need to understand whatever it may be the thing, you should remember these formulas. Okay, so first of all, Boolean algebra, we are going to discuss the first law, OR law. So R is represented here plus addition. Clear? R is represented in terms of digital, it is a addition. So in the first law, it is stated that a plus 0, a may be 1 or 0, a plus 0 is a. Okay, that is the first law. In case of a plus 1 is equal to 1, a may be 0 or 1, you are added 1 to that, you will get the 1. Next, third law. Before moving to the third law, just see this particular diagram. In that a, this is an AND gate, a bar. This a and a bar given to this particular OR gate. So you may expect it 1. How it is? See, whenever a is equal to 0, this is the a bar. Right? A is equal to 0, a bar is equal to 1. So here R is nothing but a plus, right? So a plus a bar, that is a 0 plus 1, that will be equivalent to 1. Okay, so next, when a is equal to 1, for example, a is equal to 1, a bar is equal to 0. A is equal to 1, a bar is equal to 0. That means a plus a bar, that is a 1 plus 0 is equal to 1. So a plus a bar is equal to 1. A plus a bar is equal to a plus a bar is equal to 1. This is the discussion is completed. In case of both, a plus a is equal to a. So 4 laws are clear. If it is a plus a bar is equal to 1, okay, this is the explanation for this law, and a plus a is equal to a. Okay, these 4 laws is completed. So next we are moving to the AND logic. AND here represented multiplication into, okay, product otherwise. So in this particular case, first a into 0, a may be 1 or 0, it will be 0 only. A into 1, a only. Okay, a, for example, a is 0, you will get 0. A is 1, you will get 1. So that means a value depends upon this particular product. Next, seventh law, a into a is equal to a only, not a square in this case. Okay, this is a Boolean algebra. Next, law number 8. Before law number 8, just see here this diagram. This is a, this is a bar. For example, a is equal to 0, a bar is equal to 1. The product of a into a bar, that is a 0 into 1. 0 into 1 is equal to 0 only. Next, a is equal to 1, a bar is equal to 0. So whenever a into a bar, a is equal to 1, a bar is equal to 0, that will be 0. That means whenever a into a bar is equal to 0. Okay, these up to till 8 laws are completed. Clear? Next we are moving to the next law, that is a law of complementation. So this is a very simple law, is 0 bar, that is a 0 complementation 1. It is a 1 bar, it is 0. Okay. Next we are moving to the 11th law. If a is equal to 0, a bar is equal to 1. If a is equal to 1, a bar is equal to 0. Okay. Next, commutative law. Commutative law, it is law number 14. A plus b is equal to b plus a. A b is equal to b a. Both are commutative law. Next, associative law. This associative law, a plus b plus c, these brackets are a plus b plus c. Next, a plus b, c plus d. So it is a plus b plus c plus d, and then a b c, can call it as a b c. Those are the brackets are changed, right? So that is associative law. Okay, clear? Next we are moving to the distributive law. Okay, so the distributive law here, a b plus c, just multiply distributed, a b plus b c. Next, a plus b c, that will be write it as a plus b into a plus c. You can also write it that a plus a bar b is equal to a plus b. These very important, these formulas, I can use directly these formulas while your simplification of equation, then only can solve the problem in 1 minute, right? So next, observative law. So the law number observative law, a plus ab is equal to a. How to write a plus ab is equal to a? Here common is a, 1 plus b. So 1 plus b is a into 1 plus b value is a 1. So that will be equivalent to a. Okay, this is the law. This is a into a plus b is equal to a. A into a plus b is also a. Next, law number 24. A into a bar plus b is equal to ab. Okay. So this is about law number 24. Okay. So these 7 different laws we need to remember. Total I gave 24 laws. Everyone recall these particular formulas, and then we can start your preparation for next one. Okay. Next we are moving to the equivalent switching circuits. That means how to represent it, the equivalent like on and off. 0 is nothing but a off, 1 is nothing but a on. Okay, so how to represent it both? See here. So in this particular gate, a is a off, 1 is permanently on. In this particular, a plus 1 is equal to 1. It is a on state. Okay, whenever you got a plus 1, you can write it as a 1 only. Next, second, it is a, this is a permanently off, a plus 0. A plus 0 is equal to 1, summation OR gate. Next, in this particular case, both are off, both are a on or off. You can in your hand, it maybe a will be 0 or a will be 1. So a plus a is equal to a. Okay, that is a switching. Next, this is a or operation. Always it is a parallel. Or operation is always parallel. Okay, next coming to the AND operation is always series. AND operation always series. A into 0, a into 0 is equal to 0. A into 1 already on here, a into 1 is equal to a. Clear? These are the switching operations of digital logic circuits. Next we are moving to the example problems. In this particular case, I'm take up the few formulas and then I will prove that those formulas how the values are getting. You need to remember the result in the examination point of view. Okay, a plus bc, maybe in the examination this formula is given. They are asking about a is equal to, option A is equal to ab, option B is equal to ac, option C is equal to abc, option D is equal to none of the above, for example. So you, in this particular case, I prove that AC plus BC is equal to AC. Just take it here, AC, ABC. I can take the common of AC. When I take the common of AC, 1 plus B. Just now I gave the formula to you, A plus 1. A may be B plus 1, 1 only. So any variable plus 1 is equal to 1 according to that particular formula. So I can replace 1 plus B is equal to 1, finally AC. So which option is correct? Option B is correct. In the examination, they won't provide the AC value. Okay. Next we are moving to the second one. Prove the following Boolean algebra. In the similar case, they will provide the options. In this option, this value is present. You can identify that. So I will prove that a plus bc, a plus c. Just multiply here, a into a into c, b into a, b into c. Right. So a into a, just now we learned the last, a into a is equal to a. Next one, can write it as it is remaining part. Next, you can take the common of b, for example, common of a. So a is a common, 1 plus b. Next, AC is there, BC is there. Clear? So 1 plus b already you know 1. I can replace a into 1 plus AC plus BC. Again I can take the common of a. When I take the common of a, 1 plus c. 1 plus c is also, no, 1. I can replace here, a plus BC. So what is the option now? A plus BC. Just now see here, a plus BC is a correct option. All of it clear? Next, prove the following Boolean algebra identity. So they won't provide this in the examination. You need to identify that. So y plus a bar b, I can take a into 1, a plus a bar plus b. But a plus a bar b is a one of the law, that is a plus b. You need to remember, but your understanding purpose I am going to explain this. Already a plus b bar, I gave the relation here. See here, a plus, this is a one of the 21st law. A plus a bar is equal to a plus b. Directly you need to remember that formula. Just proof I explained here. So here 1 you can replace 1 plus b, a bar b is there. Again multiply a plus ab, a bar b. Now here b is a common, a plus a bar. A plus a bar is equal to 1. That means a plus b is a correct option. Okay. Next we are moving to the example number 4. In the example number 4, they won't provide this particular part. Okay, they will give the options. So just look at the solution. Just multiply these two first of all. After that multiply with this. You will get this particular relation. A into a bar is 0. A into a bar is 0. A into a bar is 0. B into b bar is 0. A into a bar into a is equal to 0. B into b bar is equal to 0. That means any product of that particular complementary, the product of the original value is equivalent to 0. Next, b into b bar is equal to 0. What are the left thing? A into a, b, c. That means a, b, c, a, b bar, c. So a into a is equal to a into c. So remaining things you can directly write it here. Again I will take the common of B here, AC, and then B bar C is as it is. Now you can 1 plus B is the 1, AC plus A bar C. Again I can take the common of AC, 1 plus B bar. 1 plus B bar you can replace it by 1. Finally AC is the answer. Okay, what is the answer? AC. Clear? Next, one more example I am going to explain. So ABC plus A bar C plus ABC is equal to A into B plus C. So in this case, ABC, here you can write it as it is. This is the options are they will provide. So I can take the common of A and C, right? A and C. Once I take the common, B plus B bar. So remaining thing as it is. B plus B bar is equal to 1. I can replace it here. ABC. Again take the common of A. Whenever take the common of A, C plus C bar B. C plus C bar B. Just now one law, A plus A bar B is equal to A plus B. I proved that. Similarly, C plus C bar B. That means that C plus B. I can replace it by C plus B. A into C plus B. So which option? The answer is proven, A into B plus C. Okay. Next we are moving to the question number 6. And the question number 6, simplify the following Boolean expression. So this is a Boolean expression: A B C bar, A B bar C, A bar B C plus A B bar C, A B C. So in this particular case, I can take the common of A B is a common, C and C bar. So C and C bar, these two I am going to consider, right? Next, A B bar, I can take the common, C plus C, right? Next, A bar B C is as it is. C plus C bar is 1. C plus C is only C, A B C. Again B is a common here. Once I take the B is a common, what is the formula in these two? A plus A bar C. A plus A bar B is nothing but A plus B. Instead of B here, C is there. That means A plus C. You can replace here A plus C by using this particular formula. A bar B C. So again multiply AB, AC, A bar B C. So after multiplication, AB, AC, you can take the common AC here. AC. Once you take the common, 1 plus B. 1 plus B is a 1. Finally, AB plus AC. So AB plus AC is a final answer. Next, at the last question number, example 7. In this example, they are providing the A bar B is equal to A plus B. Illustrate the equivalent with help of the switching circuit. They provided the truth table. So in this truth table, A, B, A bar B, A bar A plus A bar B, A plus B. So how to write the truth table. Just now 0, 0, 0, 1, 1, 0, 1, 1. These three combinations. A bar is nothing but here 0 is there 1, 0 is there 1, 1 is there 0, 1 is there 0. Okay, clear. Next, A bar into B. That means these two multiplication. 0 into 1, 0. 1 into 1, 1. 0 into 0, 0. 1 into 0, 0. After that, A bar plus AB. So, A plus AB bar. This is addition to zeros. That is R function. 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1 only. Okay. Finally, these two combination A plus B. 0 plus 0, 0. 0 plus 1, 1. 1 plus 0, 1. 1 plus 1, 1. So finally these two are equal or not? Yes, these two are equal. A into A plus AB bar is equal to A plus B. Those two are equal with the help of this truth table. Then I will draw both the circuits. In the first R is nothing but a parallel. The first one is A, I write it here. So plus parallel, and AB, and is nothing but a series. So A bar is represented like that. Just see, I will explain here. Bar is represented like that. This is a A bar, and B is just normally B is open like that. Whenever it is a 1, it is closed. Whenever it is 0, it is open. This is a representation of switching function. Coming to your A plus B. plus is nothing but a parallel. So A and B, that is A plus B. Okay. So this is about the explanation about the different problems. Next, I'm going to give some of the important theorem, De Morgan's theorem. With the help of this theorem, we can simplify many circuits. Okay. So these laws are very useful throughout our digital electronics discussion in KVS TGT examination. So let us discuss that. Law number 25, A plus B, that is whenever we are apply the De Morgan's theorem, that will be convert, plus sign is converted into product, right? So A bar and B bar. Okay, this is the product. So next, law number 26, A B bar, this product is converted into plus A bar and B bar. Clear? So finally, what is the De Morgan's theorem? The De Morgan's theorem, according to the first statement, this is a statement, complement of sum of the product. This is a sum of the complement of sum equivalents to product of the complement. Complement of sum is equivalent to product of complement. That is the first statement. Coming to the second. The second statement says that complement of product. This is a complement. Bar is nothing but a complement. Negation. Product of complement is equivalent to sum of the complements. Complement equals to sum of the complements. Here, sum of the complements. Okay, that was De Morgan theorem. So this De Morgan's theorem, what is doing? Sum of product is converted into product of sum. Okay, so we have three cases, 3 points you need to remember while you are applying the De Morgan's theorem. So what are the three laws? You can see complementary. So complement, given the expression, remove the overall not sign. So whenever A B whole bar, we can write it as A bar plus B bar. So that is a sign convention, not removing. Not gate is that means bar, that is a complement, is removing with the help of the dot sign is converted into product sign is converted into dot. That's what here. Change all and to R. This is the AND function converting to R, and all R's are converted into this particular R is converted into and vice versa. Okay, so complement or negate all individual variables. Okay, so these 3 points you need to remember. I will explain few examples related to the De Morgan's theorem. So for example, A plus B into C plus D whole bar, that can be converted into C here plus is there, can be dotted here, A bar, here B bar. Clear? Next, here dot is there, right, that may be converted into plus. Next, C is become a C bar, and plus sign is there, that convert into dot, that is a multiplication, D bar. What is the final? A bar B plus C bar D, that is a conversion of De Morganization. This particular equation is same as this particular equation while you are applying the De Morgan's theorem. Next, once again I will take some other example. AB plus BC plus AB plus D, we can use with the help of this particular equation, simplify the equation they are asking. We are not applying any De Morgan's theorem, just simplification, same as done before examples. Just multiply this particular function with this particular function. Okay, after multiplication, AB and AB, that means A into A is equal to A, right? AB into AB is equal to AB only. Okay, next ABD, so remaining as it is. Next, AB is taken as a common. Okay, once AB taken as a common, 1 plus D. So 1 plus D is equal to 1 only. So AB is present, remaining as it is. Next one, AB is taken as a common. So 1 plus C. 1 plus C can be replaced by 1. So AB plus DC. So that is a simplified equation for this particular. Okay. So we can expect one question. Each and every paper you can see from the previous papers. We can expect the one question, this type of one question in the examination. Okay. Next one. They're asking, find the switching circuit for the following logic expressions. Maybe this type of questions you may expect it. So the first one, A into B plus C, and is nothing but a series. So A, it is a representation. Next, plus is representation, or that is a parallel. So both are parallel, B and C are parallel. So those two combination are series, right? So this is a combination of switching circuit. Next, coming to here, AB. So first case, A is there, that is a representation. Next, B bar. So that is a under. Here dot is there, and is nothing but a series. So B bar is nothing but a, this is a representation, just now I mentioned, this is a B bar representation. So this is A, this is a B bar. Next, C. This is a plus, that is nothing but a parallel. So another line, and C, this is a C representation, and this is a D representation. So finally, you know, these are the two are parallel, this is the equivalent circuit. Just what here. Next, you are trying to draw this particular this one, A bar, this is the representation, series, dot is series, B. Next, parallel, plus is nothing but a parallel. So A as it is, C as it is. Total entire combination is dot, that means series with this one, that is a C bar. So this is the final representation. Okay, so next we are moving to the this is a prove that 3 input AND gate, NAND gate, that is a A equivalent to the bubbled AND gate. So this particular logic gates is another chapter. I will explain there clearly. Just look at here. A, B, C, the product A, B, C. Bubble is there, nothing but a bar. So that will be equivalent to NAND gate is converted into NOR gate with the help of the De Morgan's theorem. So again apply the bar. A, B, C. Whole bar is converted into A bar. Here dot is converted into plus. B bar dot is converted into plus. C bar. This is the equivalent. Okay. The equivalent of NAND gate is equivalent to equivalent of NOR gate. Okay. That is a example. At the last, dual. So some of the duals are there. Duals is nothing but all ones, to zeros, all zeros to ones. So dual. So all ands are R's, all R's are ands. Just replaced. So those relations I will provide here. You need to remember that A into 0, you know, 0 only. That is the actual relation. The dual of this particular thing, this A, this plus sign, dot product, and is converted into R. So that's why R. A plus 1 is equal to 0. Next one. A into A is equal to 1. A plus A is equal to A. A into A bar is equal to 0. A plus A bar is equal to 1. A into 1 is equal to A. A plus 0 is equal to A. A into A plus B is equal to A. A plus AB is equal to A. A into A plus B, A bar plus B, AB. A into A bar plus B, A plus A bar B is equal to A plus B. These are the duals for these particular cases. Okay. So that's what the explanation of Boolean algebra. I hope that you are enjoying the class. This is a small chapter, only 30 minutes, around 29 minutes only. The video length, we can complete this particular video, then we can attend the test. Thank you.